share my screen. Yeah, so thank you for having me here. So today I am presenting my work that I did with my two partners in crime, Siebers and Schmid, from the Cognitive Systems Group of University of Bamberg. And so what is it all about? Before I want to talk about our idea of what we wanted to give you as kind of an explanation in terms of a contrastive explanation, let me quickly talk about the term counterfactuals. So what is a counterfactual? Typically, a counterfactual is a contrastive explanation in the form of negative examples, right? For a concept that only differs minimally from a given positive example. And I think a very good example here was given by Wachter et al. They said, just imagine you were denied a loan because your annual income was like £30,000. And if your income had been £45,000, if it had been, conjunctive here, you would have been offered a loan. So this is basically the counterfactual here, a minimal change in events and basically statements and facts that would give you the loan here. This is a counterfactual. And so typically where you can see counterfactuals, not the normal things here are the applications in image domains. Like for example, if you know about the contrastive explanation method by Durante et al. 2018, you can see a picture here, which I think describes it pretty good. So just imagine this is an image from the MNIST data set of handwritten digits, and the original prediction was a 3. And the system says, well, no, I think this is something different. Then you can see that the contrastive explanation method basically tells you, well, this would have been the image in order to make the prediction of a 5. Yeah, so this is the counterfactual here, just indicating what has to be the image in order to be another class, just a minimal change here. So why do I tell you that? Well, we saw that these kind of counterfactual explanations were not really present in the domain of in the relational domains, like in ILP learned models. But when you have a look in the literature, what you can see is that, for example, Winston 1970 was also presenting near-miss examples in relational domain, and he's told us that this basically results in faster learning, because if you give near-miss examples to the positive examples, then the systems would just learn faster. And so our proposal for the work was, well, what is effective for learning might also be effective for explaining a learned model. So we are in the realm of explaining models now, and I think this duality is best shown with our graph here, where we just say, in learning, normally a human teacher knows a true concept and gives examples to a system learner, and this system should then learn the concept. Whereas in explaining, we could also just say, hey, we have the human partner that wants to know some concept that is learned. And so the system explains that by giving, for example, near-miss examples as the explanation. So let me just quickly go over a few domains that I want to show you here. There's a typical family relation, a kinship relation, and we are interested in this positive example of a grandfather, Ian, which is the grandfather of Kate. And what you can see here is the models that might just have been learned by an ILP system, and what a good explanation in our case then would be for the grandfather would just be a near-miss example like Jody, which is actually the grandmother of Kate. Yeah, so just a minimal change. It's not a male anymore, it's a female. And you can also see some other things like Matt, which is actually not the grandfather, but there is a grandson relation. So by just changing all these different parent statements to to child statements, then the whole situation becomes also another misexample, which is actually the grandson. Yeah, just to wrap that up, we also had another domain, and this is an arches domain, because in the original paper by Winston, there was also this arches domain where it's basically saying, well, what is an arch? Well, there has to be something on top, and also you have to be able to go through that. So these two pillars should not meet. And here you can see some examples here, and these are the counter examples for that. So here you see that the pillars meet, and here you see that there is nothing on there, but under there. And this is the corresponding learned model for that. So don't worry, I will not go that much into detail. You can always see this algorithm in our poster session tomorrow. But quickly, what is going on here? So we have a positive example and you want to find a negative example, also with an explanation, a near miss explanation to that. And so what you do is that you first of all basically find for that positive example, let's just take the one from before, from Ian. The grandfather of Kate is Ian. Let's take that and let's first of all look at the local explanation for P. This is just a trace that you would get, for example, from Prolog. So you have seen that it's because that Ian is male, that there is a Tom, which is kind of one generation below, and then you find Kate. So this is the local explanation. And what we basically did is we just, first of all, generate all the near miss candidates. So what can there be which are actually no grandfathers? So for example, we see again in this set of near miss candidates, we can find Jodie, which is a grandmother, and we can also find some other things like, for example, Matt and Ian, which are also not in a grandfather relationship, but actually in a grandson relationship. What we then settled towards in order to find some near miss explanations, we had these rewriting filters where we could just allow to say, we can rename our predicates, for example, from male to female or from female to male or from parent to child and so on and so forth. So what this algorithm could end up with is, first of all, a so-called minimally changed clause where there is still grandfather at the head of the rule, but then all the males were actually converted to female. And so you have this new rule, female parent AC, parent CB. And what you then can do is find the near miss example by just checking for which of the near miss candidates this new minimally changed body here holds. And in this case, you actually find one, which is the grandfather Jodie Kate thing here, where you just say, now we have the female Jodie, and this is actually our near miss example. And why is there a degree? Because also our algorithm can find different degrees of near misses. So in this case, it's a degree 1 because we only changed one of our variables A to Jodie, and a degree 2 would be, well, we could change 2 or more variables, and then we could find also further degrees away from our initial grandfather example. I will quickly jump over that because I think a very important thing here is to say that we also did an empirical studio with, I think, 76 participants. I have to get the correct numbers again. But what we basically did was we had some types of explanations. For example, we showed them just a simple rule like what is a grandfather. Then we also had an example like the grandfather of Kate is Ian. And we also showed them the complete trace, but it's not the typical trace from ILP, but just a written out sentence. Like Jodie is not the grandfather, but it's the grandmother because, well, this is female and she is a parent and so on. Then we also did the same thing with a near miss. Sorry, I think I just mixed up these two. So example is, of course, the Ian one. The near miss one is Jodie and Ian, so the grandmother, and the far miss is, for example, grandson. So just further degrees away. And then we just asked the people which of these different types of explanations would be bestly fitted with the information needs. Like, for example, would it be better to have a rule for understanding the general concept, or would it be better to have an example? We also did this with understanding a particular example instance for a concept. And also a very important thing here is understanding what is not in the concept, because this can then be used to avoid in the long run false positives, right? If you better understand what is not in the concepts, then you also get a better explanation in the long run. And the first thing we did was we just took some pairwise comparisons here. So for example, what we did for the family domain, so this abstract relational domain, we found out that the people just in general found that the rule is the best thing in order to understand family. Then an example, then comes the near miss, and after that there's a far miss. So you can pretty much see here that near miss is better than the far miss of a further degree away in order to understand the concept. And this second row is then just a comparison of pairings, because we also found it interesting to see if it is better to have a rule and an example together. And for example, in this time, it was better to have a rule and example in comparison to a rule and a near miss, right? And the same thing we did for the arches. And I think it's pretty interesting to also see that for the arches here, giving an example was much more interesting than to give a rule here. But nevertheless, near miss examples is still better than giving a far miss example. I think I'm running out of time, so I think I just go a little bit quicker now. Just to give you results on just a 5-point scale. So we see here that, again, to understand the general concept, the rule is better in this abstract family domain than, of course, the exclusion here. It's best to have a near miss example out of all these different modalities. And also interesting in the arches, again, it's just flipped around, because here you can see that in order to understand the general concept of an arch, you just want to have a visual example instead of a rule, right? But still, again, near misses are best for just understanding what is not in the concept. So this is my bibliography. I hope we have some time for questions, because I'm eager to hear them. Thank you very much for having me again, and yeah, go forward with the questions.